Okay, I think we're in section 14 now. Yeah, we're at 14, and this could be the section on Taylor polynomials. We're going to go through it. As we go through it, I'll certainly go to the whiteboard. I'm not going to read verbatim to you, but I would recommend, make some attempt to read what we're giving you. All right. In the future, when you take a course at another school, particularly university, the teachers would be expecting, without telling you, that you're expected to read things before coming to the classroom. Now, typically, historically, what people read before going to the classroom was a textbook. Now, sometimes they're going to be, articles or maybe something the teachers prepared, whatever, but you're reading something before coming to classroom. It makes a classroom activity more productive. If you're just showing up unaware of what's going on, it's going to be a lot of, drudgery for you. And that's what we're not looking forward to. We're looking forward to getting engaging careers. But I'll go through the notes page by page. We'll talk about, polynomial approximations to curves. I'm not going to read it to you, but I'll go through the work. And certainly as I go through the work, I want to point out it's tedious. All right. But eventually, at some point in the tedium, you start to see patterns, and we want to get to those patterns. All right. I know it's incredibly difficult, though, and I will talk through that. I may not write down everything that's in the notes, but we do want to get to this point where we get a general pattern of what we're talking about. So the point of going through the drudgery is to get a general pattern. All right. And that's our goal, to get a general pattern. Again, I may not do all the excruciating details, but those details should be worked through. And eventually, when you work through all those details, we will eventually get to a problem set where I go through the examples. After I do the examples, then it would be expected that you do the supplemental exercises on your own. And again, seek out help if you do need it. All right. So I'm going to switch screens. Give me 1 second to do so. And we'll talk through it. All right. So I got to share a screen with you, don't I? Okay. Hopefully you're seeing the whiteboard. All right. So it's going to start off, basically saying that, the sine function, which is something you're very familiar with, it says that it can be written down with this, looks like a polynomial to me. So I'll just go through that with you. It looks like they say sine of x equals x minus x cubed over 3 factorial plus x5 over 5 factorial, yada, yada, yada. By the way, when they put these 3 dots down, they say it's pretty predictable. So if it's predictable, what would the next term be? Well, just looking at it, if I thought about it, what would the next term be? I'll write this down for you. Looking at the bottom, they're all factorials, by the way. And I'll write this over here. This looks like it might be something. I'm going to say 1 factorial here. So 1, 3, 5, 7, 9, 11. Looks like it's going up by 2, right? So 11 up 2 would be 13 factorial. And then x13 up here. Right? If someone said, what's the next term going to be? Well, if this pattern is predictable, I would say 15 factorial. And it's going to be minus because it's going back and forth, plus minus x to the 15. And you could do this all day long. That's not our point, by the way. Our point is, does it really work? Does this really work? This would be x17, x17 on top. You get the idea. So what they do is they start to graph this thing out. And as I do this over here, I'm not claiming that you get kind of dizzy looking at it, but they say this is the sine function. Well, I'm kind of looking at it and I'm saying this, one of those curves is the sine curve. So if you're looking at it, I hope you realize they're color coded. All right. So it may not the best colors of choice, but I know that this is not a sine function. That's a straight line, right? I know this one's not sine. This one's not a sine function. That one clearly not a sine. And then I got these 3 over here. And looking at them, I'm going to look at those things and I'm wondering which one of those would be the sine function. And that might be tough to do. All right, looking at that, not knowing it is, but I'm kind of looking at the sine function. I know what it looks like, sort of like this over here. And I'm going to say it looks like this curve here. So I'm going to say this one here looks like the sine function to me. All right. Then the question comes is, what are the other guys? The other guys are related to these polynomials up here. All right. So if I were to write this one down over here, this is a line, by the way. What would it be? It would be y equals x. That's that guy right there. What's the next one going to be? It's a cubic problem. So the next one's going to be y equals x minus x cubed over 3. So do you see the cubic there? Let's take a look at it. And I think I see the cubic, and it's this curve right over here. All right, let me point that out to you. This looks like the cubic to me. That looks like the cubic over there. All right, what's the next one? Fifth degree polynomial. Boy, they're getting tough, aren't they? So the next one's going to be y equals x minus x cubed over 3 factor. I'm sorry, it's 3 factorial plus x5 over 5 factorial. By the way, machine drew this, so that's what makes it a little bit easier for me to deal with. So I'm looking for that fifth degree polynomial, right? I know it's tough. And I'm going to say it looks like that purplish curve over here. All right. So I'm going to say it looks like this one over here, purplish curve. Now, my claim over here is what's happening. And what I want to claim over here is looking at the picture, the sine function is a sine function. Now the line fits it pretty good near the origin. And then that, the cubic one, I'm sorry, I think I made a mistake. The cubic one is actually the green one. I got to correct it. And let me go back over here. I didn't see that. I'm a little colorblind here, I guess. Nice excuse though. So I got the line, and let me point this out over here. The green curve is the cubic. Okay. And then the next one up, the red curve, I got to look at that one over there. No, the purple curve is the fifth degree. So I'm okay with that. So they're kind of separating things out. It's kind of hard, but what I'm getting across to over here is that it wasn't so much separating out, but what I'm claiming over here is that every single curve that we put down, and it says, we put a bunch of them down there. I'm not going to count them up for you, but they all seem to fit really nicely around the origin. But then when we start to spread out, most of the curves start to move away from the sine function. All right, so I'm going to say this blue curve here moves away pretty quickly. Then this green one looks like the next one that moves away, right? So I point this out. The blue one is the line. The green one starts to move away from the sine function. That's the cubic. And then which one moves away? The purple one moves away. That's the fifth degree. Then what's the next one to move away? That'll be the seventh degree polynomial. And then the next one to move away would be the ninth degree polynomial. Then the next one to move away would be the 11th degree polynomial. So as the degree goes up, the fit gets better, but it does move away. It does move away. So what we say is that, that's an interesting concept. How did they come up with that? And that's the tough part. All right, that's the part we want to get to. How did they come up with that? How did they do that? So I'm going to say it's something that I'm going to kind of accept what they did. I don't know what they did, but I'll kind of accept it. So the thing about this over here, if this is true, I bet there's something I could do with this to find another one. And I want to write that down for you. And we'll go to the next page in a second. I want to differentiate both sides. Let me write that down for you. So if you differentiate both sides of this with respect to x, so I'm going to differentiate both sides. What's your left side? Cosine of x, right? I bet this is going to be easy to differentiate. What do you get? 1 minus 3x squared over 3 factorial. I'll simplify later. Plus 5x4 over 5 factorial. My goal in life is to see patterns, by the way. Not to pretend I see things, but I want to see if I see things. I'll write this one down. Oops, sorry about that. Cosine x, 1 minus x squared, 1 and 3's cancel, 2 factorials, plus x4 over 4 factorial, minus x6 over 6 factorial. Well, this looks pretty simple now. I think I got it covered. But again, where'd they get that from? And is this true? That's another problem. but I think I could write the next term down. And what do you mean by that? It plus minus x12 over 12 factorial minus x14 over 14 factorial, yada, yada, yada. I think you get the idea. Now, does it make sense? I don't know. I don't know where they got that sign thing from. And someone says, well, that's just a given. Maybe that's just the way it is. All right. And then the next question is does it fit if I keep going out? Well, it appears the fit gets better and better as I go out. Now, I wonder if it's true for cosine. Well, if it's true for sine, it's probably true for cosine too. All right, next page. But again, still this is how you got them. So I'm going to say they just did that over there. So now what do? They do something like, to derive this guy over here, and I got to kind of read it to you. It says, find a quadratic approximation, px equals a plus bx plus cx squared. I think I should write that down. So px equals a plus bx plus cx squared. And they want this to be an approximation of the function f of x equal cosine x. Well, you know what? From my example, I think I know what it should be. So if f of x is cosine x, from the example we just did, p of x should turn out to be what? Well, let's look at it. It should turn out to be 1 minus x squared over 2 factorial, which is basically just 1 minus x squared over 2. All right. Now, I don't know if that's true, by the way. So what I'm going to do over here is talk about the technique, and I'll read it to you. It says it should satisfy the conditions at a equals 0. But furthermore, it should also satisfy the derivatives going forward. So I'm going to start writing derivatives down over here. And we want to, say this thing is centered at, I'm going to say x equals 0. Let me go back over here and point out what I mean by that. If you look at our graph seems to sort of like, everything seemed to work so nicely at 0, and everything kind of spread away from the 0. So this is also centered at 0. All right. By the way, we like centering things at 0. It makes it easy for us. We don't have to. We can center it elsewhere. So let me write this down over here. P prime. Well, that's going to be b plus 2cx. I'm going to write p double prime, and that's going to be 2c. Now, if I put down p triple prime, that's going to be 0. Well, let me write this down. And by the way, they have to agree. And I have suspicions. I'll tell you what the suspicions are again. This is my suspicion. That's going to be my answer. So let's write this down. F prime of x. That's minus sine, right? F double prime of x. And what would that equal? Well, that's minus cosine, right? And F triple prime of x, we'd be back to what? That would be sine, right? I think you get the idea. Now, I want to make sure these things agree. So what I'm going to do is I'm going to write this down now. So what's P of 0? It's A. What's F of 0? What's cosine of 0? It's 1, isn't it? So now I know A is 1. I know that much. All right, let's keep going. Let's do P prime 0. What's that going to be? That's going to be, what's that going to be? Just B, right? What's F prime of 0? Well, I'm looking at it. That's sine of 0. That's 0. So I know B is 0 now. Let's do P double prime of 0. This is tough, isn't it? Well, it's just 2C, isn't it? And what's F double prime of 0? Well, I don't know. I got to check it out. That's minus 1, isn't it? So what does it say? 2C is equal minus 1. So that says C is minus 1/2, right? Let's write that down. So let's write it over here. What's P of X? Well, I found A to be 1, right? Remember what we did. A is 1. B was 0. I'll put down 0x. And then C turned out to be minus 1/2. Let me write that down. Minus 1/2 x squared, right? Is that what we said it was going to be? It sure is. What do we get? 1 minus 1/2 of x squared. Worked out beautifully. All right. So this is a nice technique. What are they doing? They're taking polynomials and they're fitting it by looking at the function, evaluate at some value, derivative evaluate some value, and everything's got to be in agreement. All right, everything. All right, let's go to the next page. And again, what they do over here, they draw a picture of it. All right. I want to tell you what the picture is a picture of. It's a picture of the cosine curve. This is the cosine curve. And then the polynomial they're writing down, I'll tell you what the polynomial is again. If it's linear, it would be, the first one would be 1. If it's quadratic, what's it going to be? P is equal to 1 minus x squared over 2. Well, if you look at the line y equals 1, that's over here. It fits it, but not very nicely, only near 0 in a very small band. What's this a graph of? It's a graph of, y equals 1 minus x squared over 2. And it's quadratic. And the quadratic fits even better. Now, if you go to the next fit, would be a 4th degree polynomial, it would even get better and better. And that's where we get the next thing up. And I know it's difficult. I find this to be incredibly tedious. So it says, now we'll repeat this thing for even a higher degree polynomial. And I want to write it down for you. As I write this down for you, it's going to require work. Right? So I'll put the P of x down. And that's going to be, and again, I got to make sure I'm using the same letters. Yeah, I'll put this down. A plus bx plus cx squared plus dx cubed plus ex4. Well, I want to be honest with you. I hope you remember that we think we know the expansion for cosine. And if I went to the 4th degree one, it's going to be 1 minus x squared over 2 factorial. There'd be no cube. Then it would be plus x4 over 4 factorial. What's 4 factorial? 4 times 3 is 12 times 2 is 24, right? So I'm expecting to see that. Again, what I expect to see, what I'm going to see might be 2 different things. And what am I going to write down? Derivatives now. I'll be very careful to do this, by the way. What do you get over here? No, what does A differentiate to? Nothing. I'm not going to put A down. That would be crazy. Let me erase that. It's going to be B plus 2cx plus 3dx squared plus 4e x cubed. Let's put P double prime down. It's going to be tough. Polynomials are easy to differentiate though. What are you going to get? 2c plus 3 times 2 dx plus 4 times 3e x squared. There's a reason I'm not multiplying things out. What's that going to be? 3 times 2d plus 4 times 3 times 2ex. I'm going to keep going. When we get to the 4th derivative, we don't use hash marks. We put the 4 in parentheses. What would that give me? 4 times 3 times 2 times e. That's pretty simple. All right. Now let me go over here. There's a lot of writing. I'm going to write down what f of x is. What's that going to be? Cosine of x, f prime, minus sine of x, f double prime. What's that going to be? Minus cosine of x, f triple prime. What's that going to be? Sine of x. F4, what's that going to be? Cosine of x. All right, it's tough. I'm not going to say it's going to be easy for you, but I got to write this stuff down. What's P of 0? That's just A, right? What's P prime of 0? Wow, that's easy, just B, right? You see that? Pretty simple. What's P double prime of 0? Let's see, it's just 2C, right? What's P triple prime of 0? That's 3 times 2 times D. What's P4 0? 432E. I'll put it over here. 432E. Now I'm going to do something that's going to disturb some people. I'm going to write these down in what I believe is a pattern. This is 4 factorial times E. This is 3 factorial times D. This is 2 factorial times C. This is 1 factorial times B. And this is 0 factorial times A. I want to point out what I think I'm seeing. Like 4th degree, 4 factorial. 3 degree, when I say degree, I'm talking about the number of derivatives. 3 factorial, 2 factorial, 1 factorial. This is no derivative, 0 factorial. I got this over here. This is a real nice simple pattern, by the way. Now, what I'm going to do now is I want to make sure these are matching up. All right. So I want to, and it's not easy. I got to remember. And let me go back over here and let's write this down. And I'm going to write it over here. So what's F of, what's F of 0? What's cosine of 0? It's 1, right? And what's F prime of 0? Well, that's going to be 0, isn't it? That's pretty simple. F double prime of 0. That's going to be -1, right? F triple prime of 0. That's going to be 0. What's the 4th derivative going to be evaluated 0? It's going to be 1. Let's go back over here. And I'm starting to realize that these things need to be in agreement, that these things need to agree with each other. And I'm going to say it should be pretty easy to do. For example, what would A be equal to? And I'm equating these things, right? What would A be equal to? It would be 1 over 0 factorial. Let's write down what B would be equal to. B would be equal to 0 over 1 factorial. Right, we'll talk about that, what that means later. What's C equal to? -1 over 2 factorial. All right. What's D equal to? 0 over 3 factorial. What's E going to be equal to? Well, I don't lose sight of it. It's going to be 1 over 4 factorial. All right, so someone said, I have no idea where this is going. It's going to find a polynomial, and we want to find this. Let's write it down for you. And as I write it over here, I got to be careful when I'm writing it down, right? So it's going to be P of X. I'll write down again, it's A plus BX plus CX squared plus DX cubed plus EX4. Let's write this down. What's A? It's 1. It's right here. Now, if you want to write this down, that's fine, but I'm going to clean it up later. What's B? I'll write that down. Plus, I'm going to put X0 over here for you. I just did B. What's C? Well, it's -1 over 2 factorial, right? And then X squared. Plus, what's D? It's 0 over 3 factorial. And then what do you get? You're going to get X cubed. And then you're going to get plus 1 over 4 factorial X4. All right, I'm going to clean this up a tiny little bit, but I definitely see a pattern to this, and I hope you see it too. All right, so what's P of X equal to? And we'll check it with our suspicions. It looks like 1. That's this term. There's nothing there. Then it looks like -1/2 of an X squared. I think I've seen that before. This guy's going to be 0. And then what do you get? Plus What's 4 factorial? 24x4. All right, let's go back. I want to make sure, keep that in the back of your mind. And I think we said that before, remember? What I say, I was expecting to see this. Now, why is that? That's how we started our conversation. We started with sine, we took a derivative, and we were seeing that pattern over there. So I'm going to say that's a really nice, simple pattern to come up with. Do you notice there's factorials involved in it? There sure are. All right, there's factorials in it. All right. So I kind of, maybe write down what I'm seeing over here. And again, I'm not saying it's perfect, but this looks like, f of 0, x to the 0 over 0 factorial, that's this term, plus f prime 0, x to the first power over 1 factorial, plus f double prime of 0, x squared over 2 factorial, plus f triple prime. This is going to take time and effort on your part, by the way. X cubed over 3 factorial plus f4. Remember, once we got to 3 hash marks, we stop using hash marks. We put in parentheses, which means the forced derivative, x4 over 4 factorial. Could I keep writing this down? You bet. f5, x5 over 5 factorial, yada, yada, yada. We can do that for a very long time. All right, I'm going to say that's pretty much done. If you go to the next page, though, all the work is down there for you. And I know it's a lot of work. Let's look at the picture. And what's the picture going to be? Well, they're putting everything down for you. So what's down over here? I want to point out, this is the cosine curve here. All right, what's this one over here? This is the line y equals 1. That's the first term. What's the next one going to be? The quadratic. What's quadratic? Y equals 1 minus x squared over 2. And what's next guy going to be? It's going to be that 4th degree polynomial, which is, let me make sure I'm doing that right. Yeah, this one over here. And that's going to be what? Y equals 1 minus x squared over 2 plus x4 over 24. And yeah, I used the machine to graph that out. By the way, they do talk about, if you want on and on and on, which I just discussed with you, the pattern's going to be this over here. What was I saying? That's the pattern to it. And the pattern is, if you were going to do that, you would be getting this thing over here. What's on bottom? 2 factorial, 4 factorial. You can check it on a calculator, 6 factorial, 8 factorial, and that's 10 factorial. All right. So let's take a look at another example. And again, you might say this is really kind of tedious to do. And I agree, it is tedious. It's something that's so tedious that it almost bothers me to write it down, but I'm going to write it down. And what do you get? P of x, and that's a plus b x minus 1. This one's centered at x equals 1 now. All right, let's keep writing this down. I'm just writing down what I'm seeing. C x minus 1 squared plus d x minus 1 cubed plus e x minus 1 4. Now someone says, what's the easy value to evaluate p at? I'd have to say 1. So I want to write that down for you. What's p of 1? Let's not lose sight of that. That would just be a, right? Let's not lose track of this. Let's put down p prime now. What's going to be b? Maybe I'll put it right below it. I don't want to get too crazy with this. That would be b. Well, I'm doing the first derivative now, by the way. Plus 2c x minus 1 plus 3d x minus 1 squared. Part of this learning is just doing some legwork, exercise, so to speak. This would be 4a x minus 1 cubed. And what's p prime at 1? Well, a lot of things disappear. I'm just left with the b. I'll put that down over here. Sorry about that. My screen's a little bit jumpy today. I actually think it's my pen. Let's put down p double prime. What's that going to equal? 2c plus, what would that be? That would be 3 times 2 times d, right? X minus 1 plus 4 times 3, x minus 1 squared. And I'm going to put down p double prime of 1. And what would that be? That's just 2c, right? Let's keep moving. Let's put down p3 now. And what's that going to be? 3 times 2 times d plus 4 times 3 times 2, x minus 1. And I think I could put down p triple prime of 1, right? What would that be? 3 times 2 times d. Whoops, right, not 32, 3 times 2. Let's do it down p4 now. And what would that be? That would just be 4. You know what? I lost the e somewhere. Sorry about that. Let's write that down. And so p4 evaluated at 1 would be 4 times 3 times 2 times a. Well, you know what? I'm always looking for patterns, and I'm going to write them down for you now. 4 factorial e, 3 factorial e, 2 factorial e. I'm sorry. I got e in my brain now. I got to erase that. That's d. Sorry about that. 2 factorial c. This would be 1 factorial b, and that would be 0 factorial a. We saw that before, by the way. All right. And now it seems strange that we're seeing these things over and over again. And what are we seeing? You know, the 4th derivative, 4th factorial, 3rd derivative, 3 factorial. Again, I'm not saying I know what e is at this point. 2 factorial, 1 factorial, no factorial. Now, what are they trying to fit it to? So I don't know. I have to read it. They're trying to fit this to a 5th degree polynomial. And I'll write that down, x5 minus 4x squared. I'm going to be real careful here. So f of x equals 5x 4 minus 8x. F prime, I'm sorry, I did it again. F of x, I didn't mean to do that. I got derivatives in my head. I should concentrate though, right? 5x4 minus 8x, f double prime. What would that give me? 20x cubed minus 8, f triple prime. What would that equal? 60x squared, f4. What would that equal? 120x. Now, by the way, I hope you remember that this was centered where? At 1. Remember, we evaluate this at 1? We need to evaluate these at 1. So I'm going to write this over here. What's f of 1? F of 1 would be 1 minus 4, right? 1 minus 4 is minus 3. We'll do that later. What's f prime at 1? Well, that would be 5 minus 8, which is minus 3. see if I did that right. 1 minus 4 is minus 3. 5 minus 8 is minus 3. Wow, that's a miracle. F double prime of 1. What's that going to equal? 20 minus 8 is 12. F triple prime at 1. That's going to be 60. Whoa, that's crazy. And what's that? This F prime is going to be 120, right? I'm running out of room, so I got to put it over here. So F4, the value at 1 is 120. So what do I know now? I know this. Let me write this down. So 0 factorial A is minus 3. I'm going to write them down separately. 1 factorial B is minus 3. 2 factorial C is equal to 12. 3 factorial D is equal to 60. And 4 factorial E is equal to 120. Now, someone says, what are you really looking for? I'm looking to get the A, B, C, and D. And I think you can write it down now. So what's A going to be equal to? I'll put it over here. Minus 3 over 0 factorial. What's B equal to? Minus 3 over 1 factorial. I keep writing these down for you. What is C equal to? 12 over 2 factorial. What's D equal to? 60 over 3 factorial. I'm not going to simplify until later. What's E equal to? 120 over 4 factorial. All right. Now I'm going to, communicate to you what these things are to me, looking at them. This is going to be F evaluated at 1 over 0 factorial. This is going to be F prime evaluated at 1 over 1 factorial. This is going to be F double prime evaluated at 1 over 2 factorial. This is F triple prime evaluated at 1 over 3 factorial. They got a very nice pattern to it, which is going to be F4, that's the fourth derivative of 1 over 4 factorial. But I also want to simplify it for you. And what's this one going to give me over here? Minus 3. This gives me minus 3. This gives me 12 divided by 2, which is 6. That would be 20 divided by 2, 10. I'm not going too fast over here. 4 factorial is 24, right? 4 times, let me do 3 factorial. 3 times 2 is 6, 10. 4 factorial is 24. 24, you get 120 by 24. 12 is 2, and 10, 5. All right, let me get my eraser out. Sorry about the arithmetic on the problem. Shouldn't be doing that in front of you. All right, so someone, what are you doing over here? You can't remember? Look back. It's a lot of work though. We're trying to do this. And I'm going to pull it over here. 1 second to do so. Sorry about that. Not sure where that A came from anymore. Oh, I'm sorry, it was over here. My fault. And let me pull this over here. Pull this down here, push this up. Boy, this is a big piece of paper, man. And let's write it down. So what's P of X? What's A? It's minus 3. What's B? B is minus 3. I'm going to erase that. I'm just putting this down, by the way. What's C? 6, x minus 1 squared. What's D? It's 10, x minus 1 cubed. And that's 5, right? Plus 5, x minus 1, 4. This is going to be an approximate fit to the curve f of x equals, well, you can't remember, we'll look back up, and it's going to be x5 minus 4x squared. Right, it's an approximate fit. Now someone says, why do you know it's an approximate fit? Well, this one over here is a fourth degree polynomial. This one here is a fifth degree polynomial. Now the big question becomes is, could I have gotten it wrong? You're not kidding, I could get that wrong. But before I do that, I want to write down the pattern I'm seeing. And I'll write it over here for you. F of 1 over 0 factorial x to the 0 plus f prime of 1 over 1 factorial x minus 1 to the first power. Next one, what do I see? I see f double prime evaluated at 1 over 2 factorial x minus 1 squared. This is going to take time and effort on your part to see this, though. That's where the exercises come in. You got to exercise to see this. And that's going to be cubed. And the last one we did was evaluate at 1 over 4 factorial x minus 1 to the fourth. You may find this curious, though. The actual p of x, if I took it out 5 times, let's write that down now. If I did it 5 times, that would be f of 1 x0 over 0 factorial. This is very easy to write down, by the way. F prime of 1 x minus 1 to the first power over 1 factorial plus f double prime 1 x minus 1 squared over 2 factorial plus f triple prime evaluate 1 x minus 1 cubed over 3 factorial plus the fourth one derivative, evaluate 1 x minus 1 to the 4 over 4 factorial. One more to go, plus f the fifth derivative, evaluate 1 x minus 1 to the fifth power over 5 factorial. This one here is exactly equal to f of x. It's going to be a fifth degree polynomial. Now someone says, I don't believe that. Well, you know what you do then? Do the work. Do the work. Expand it out. And when you do that, you're going to find out after all that work, you're going to get x to the 5 minus 4x squared. It's worth a try. It's worth it. It's remarkable. All right, let's keep going. And that work is over here. By the way, I'm going to copy this for you because what we're trying to emphasize for you guys is, verification of what we're saying is true. And again, you can't always trust people. I hope you can trust me a little bit. Next page, prior page, I'm going to paste that in. Sorry about that. What's over here? And I'm going to go back to my work. Sorry about that. I'm kind of screwing up here. Let me get my red pen out. Everything's working fine as advertised. All right, what else do? I graph it out. Someone says, what are you graphing out? I'm graphing out 2 different things. I'm graphing out f of x. What's f of x? It's x5. I can't remember what f of x was. Oh, minus 4x squared. That's a fifth degree polynomial. And I'm also doing this one over here, which is a fourth degree. I hope you can differentiate the two. All right. So I'm going to just put arrows in over here. This curve here is the fourth degree polynomial. It's crazy looking though. All right. That's the fourth one over here. It goes down over here and it comes wraps up like up here. What's this one over here? I'll do it in red. It's the fifth degree one. It looks like this over here. So the number one, this thing fits really nicely on some interval around 1. Where does it not fit so nicely? When you move over here somewhere, it starts to move away. However, I want to point out, expanding this one more term, it would be an exact fit. P of x and f of x would be exactly fit. The point of giving you graphs, though, is for you to look at the graphs and find out how remarkable what we're doing is. All right, fitting things, polynomials to polynomials in some cases, polynomials to transcendental functions in other cases. So we're hoping after, the lesson that, you're starting to think about the patterns that I've described to you. All right. So I want to claim, and I'll go through this, that we have really nice, simple patterns over here. And I'm hoping you're seeing that. And again, I'm not saying to see it immediately. It takes time and it certainly takes effort. So these are Taylor polynomials. And we're talking about general patterns. So, general patterns for a Taylor polynomial near the zero. What do you mean by that? We're centering it at zero, would look like this over here. All right. If you go to degree 2, what does it look like? This guy over here. Now, when I write this over down, you remember when I wrote it before, I wrote it a little bit differently. I wrote that this one would be f of x, and I would write down, an approximate fit for that would be f of 0. Then I'd write down x0 over 0 factorial. It's the same thing they've written down. The next one is going to be f prime 0 times x to the first power over 1 factorial. And if I were to write this one down over here, I probably would have written it a little differently. I would have written down f of 0, x to the 0 over 0 factorial plus f prime of 0, that's a prime, x to the first power over 1 factorial. And if I keep going, what's the next term going to be? F double prime 0 x squared over 2 factorial. And we've derived that before, by the way. So then the big comes over here is that, you could do this in general, but I'm hoping that we've done so many already that you're starting to realize that these patterns do emerge. And I want to point out the pattern that we've discovered just by chance, so to speak, but you can work through that arbitrary one as well, where they're giving you the C's. Let me put this over here, expand this out. This is really important. A real simple pattern. You want to know that pattern. I'm going to write in the things some people like to write in for these guys over here. They like to write a fraction bar in because they want everyone to look like a fraction. So 0 factorial and 1 factorial. All right, what am I noticing? A real simple pattern. That's the first power. If you put an x there, that would be x to the 0 over here. So a real nice pattern. This can actually be written down as a sum. So f of x, sum, fraction, f, evaluated at 0. I put the n here. What does that mean? Well, if n is 0, what's the function? If n is 1, first derivative, if n is 2, so forth and so on. What goes here? N factorial, and then x to the n. And this would be n equals 0 to whatever number you're going to go to, some finite n. In this case over here, there's some finite n you're going to. The next page, the one that's centered at a different value. Again, we did an example like that. And also it turns out pretty nice. What I mean by that, it's going to look like this over here. All right. You want to know that from the examples. People don't see this immediately, though. It takes time to get there. I'm going to write in the fraction bar, though, because I want it to make it look very consistent. This would be 1 factorial. This is the first power. This would be 0 factorial. What would go there? X minus a to the 0 factorial. I'm sorry, to the 0. I'm sorry, I didn't mean to say 0 factorial, to the 0. All right, nice, easy pattern. All right, so what do we do now? This is new. There's no doubt about it. This is something you have not seen before. I know when I used to teach Calc 1, I would do it for fitting polynomials, but then it didn't go over too well. And but it's really the same technique that the Calc 1 book would do as well. But now we're in Calc 2. So next thing up is examples, and we're going to go through the examples one at a time. All right, as we do that, I'm going to say it's really nice if you have the patterns down, and that way we don't have to put these coefficients and figure it out. We have patterns to do. All right, thank you for your attention. Again, once we get through the examples, you want to try on your own. And again, if after all you're trying and studying, you can't get something, please, I want to encourage, come by during office hours, and I'll be more than happy to help you.